Quantum computers are a revolutionary new type of computer that harnesses the principles of quantum mechanics to tackle complex problems that are impossible for traditional computers. Unlike classical computers that use bits, quantum computers use qubits with unique properties that enable fundamentally different calculations. Classical computers use bits to represent information as either 0 or 1. These are the fundamental units of classical computing, allowing computers to process data through logical operations. Quantum computers use qubits instead of bits. Unlike classical bits, qubits can exist in a state of superposition, meaning they can represent 0, 1, or both values simultaneously. This superposition allows quantum computers to explore many possibilities at once, processing vast amounts of data in parallel. The block sphere visualization shows how qubits can be in any combination of 0 and 1 states. Here's a comparison of classical bits and quantum qubits across different tasks and physical implementations, showing their trade-offs in coherence, speed, and cost. The key advantage of qubits is their ability to be in multiple states simultaneously, enabling quantum computers to solve certain problems much faster than classical computers. Superposition allows a qubit to represent multiple states concurrently. Imagine flipping a coin. It's either heads or tails. A qubit in superposition is like a spinning coin, existing as both heads and tails until observed. This exponentially increases the computational possibilities. Entanglement is another key quantum property. When two qubits are entangled, their fates are linked. Measuring the state of one instantly determines the state of the other, regardless of the distance separating them. This spooky action at a distance, as Einstein called it, enables complex correlations and computations that are impossible with classical systems. Quantum interference is a key phenomenon in quantum computing, where quantum waves can either reinforce each other through constructive interference or cancel out via destructive interference. Quantum algorithms leverage this interference to amplify the probability of finding correct solutions. Incorrect paths destructively interfere, reducing their likelihood, while correct ones constructively interfere, increasing their amplitude. Through this precise control of interference, quantum computers can efficiently solve problems that are difficult for classical systems. Similar to logic gates in classical computers, quantum gates are fundamental operations that manipulate qubits. These gates perform specific transformations on the quantum state, guiding the computation towards the desired outcome. At the end of a quantum computation, qubits in superposition must be measured. This process collapses the qubit to a definite state, either 0 or 1, providing the classical result while destroying the quantum superposition. Measurement is probabilistic. The outcome depends on the amplitudes in the superposition state. Each measurement gives a random result based on these probabilities, so algorithms often require multiple runs to obtain reliable results. Shor's algorithm is a famous quantum algorithm that can factor large numbers exponentially faster than the best-known classical algorithms. This poses a threat to widely used encryption methods like RSA, which rely on the difficulty of factoring large numbers. Shor's algorithm leverages quantum superposition and entanglement to factor numbers. It initializes qubits in superposition states and uses controlled operations to find the period of a mathematical function, which reveals the factors. Unlike classical computers that process bits as 0 or 1, quantum computers use qubits in superposition, allowing parallel processing. This exponential power makes Shor's algorithm a serious threat to current encryption standards. Since RSA encryption depends on the computational difficulty of factoring large numbers, Shor's algorithm could break these security systems once quantum computers become powerful enough. Grover's algorithm revolutionizes how we search through unsorted databases by providing a quantum advantage. Classical computers use linear search for unsorted databases, requiring up to n steps to find a target item among n possibilities. For example, searching through a database of 1 million items could take up to 1 million checks in the worst case. Grover's algorithm offers a quadratic speedup over classical search. Instead of checking items one by one, it uses quantum superposition to evaluate multiple possibilities simultaneously, requiring only the square root of n steps. The algorithm begins with qubits in superposition, representing all possible database items simultaneously. This parallel evaluation is the key to quantum speedup. Through amplitude amplification, the algorithm iteratively increases the probability amplitude of the correct answer while decreasing amplitudes of incorrect ones. After approximately Qn iterations, measuring the qubits reveals the target item with high probability. Although Grover's algorithm provides quadratic rather than exponential speedup, it still offers substantial advantages for search-intensive applications, making it valuable for optimization problems, machine learning algorithms, and large database searches. Quantum computers excel at simulating quantum systems, such as molecules and materials. This capability enables precise modeling of chemical reactions and material properties that are impossible or impractical for classical computers. Quantum computers are also promising for optimization problems. In areas like financial portfolio optimization and supply chain modeling, quantum algorithms can explore vast solution spaces much more efficiently than classical methods. Finally, quantum computing enhances machine learning algorithms. Through quantum machine learning and variational quantum algorithms, quantum systems can process high-dimensional data and train models more efficiently than classical approaches. Quantum computers are currently in the noisy intermediate scale quantum, or NISQ, era. This phase is characterized by quantum processors with 50 to 200 qubits that perform calculations but are prone to errors without full error correction. While NISQ devices have limitations, including their small qubit count and susceptibility to noise, they offer significant promise. These systems are essential for testing quantum algorithms and advancing error correction methods that will enable larger fault-tolerant quantum computers. Hybrid quantum classical approaches are particularly important in the NISQ era, combining quantum processors with classical computers to tackle complex problems. NISQ systems are also enabling progress in quantum machine learning and neural networks, where quantum circuits can process data in ways that classical computers cannot match. Developing error correction techniques is crucial for moving beyond NISQ limitations. Research in quantum error correction is making rapid progress, with surface codes and other methods protecting quantum information from noise. Superconducting qubits represent one of the most promising approaches to building quantum computers. These qubits use superconducting circuits, materials that conduct electricity without resistance when cooled to extremely low temperatures. A superconducting qubit consists of tiny electrical circuits that can exist in quantum states. Unlike classical bits, these qubits can be in superposition, representing both 0 and 1 simultaneously. Major companies are advancing this technology. IBM has developed processors like Condor with over 1,000 qubits, while Google uses superconducting qubits in systems such as Sycamore. This roadmap illustrates the rapid progress in superconducting qubit technology, showing IBM's Condor processor and future systems with increasing qubit counts. These advancements in superconducting qubits are pushing quantum computing toward practical applications, though challenges like error rates and decoherence remain. Trapped ions represent another promising approach to building qubits. In this technology, individual ions, such as calcium or ytterbium atoms, are confined using electromagnetic fields. These trapped ions serve as qubits, with their quantum states controlled and manipulated using precise laser beams. Companies like IonQ have advanced this technology, reaching systems with 32 qubits that demonstrate remarkably high fidelity. Fidelity refers to accuracy, and trapped ion systems often achieve error rates below 1% per gate operation, which is superior to many superconducting alternatives. Developing quantum algorithms requires specialized software tools. Frameworks like Qiskit from IBM and Cirq from Google provide programming languages and libraries for working with quantum computers. Cloud platforms like IBM Quantum Experience and AWS Breakit offer remote access to quantum hardware. Quantum error correction is crucial for building fault-tolerant quantum computers. Qubits are very sensitive to noise and disturbances, which can introduce errors during computation. Qubits exist in superposition, but environmental noise can cause them to lose their quantum state. This decoherence introduces errors that corrupt calculations. Error correction techniques use redundant qubits to detect and correct mistakes. The surface code is a leading approach, using a grid of physical qubits to encode logical qubits that are resistant to errors. Recent advances have improved gate fidelity to 99.9% in leading systems. Experimental demonstrations like this study of coupled spins show how error correction techniques are being tested and refined in real quantum hardware. Without error correction, quantum computers remain limited to noisy intermediate-scale devices. With it, we can build fault-tolerant systems capable of reliable, large-scale quantum computations. Combining quantum and classical computers provides significant benefits in the near term. Hybrid algorithms leverage the strengths of both types of computers, using quantum processors for specific quantum tasks, while classical processors handle the remaining computations. This approach allows quantum systems to focus on tasks where they excel, such as quantum simulation and optimization, while classical computers manage error correction, data preprocessing, and result interpretation. For example, a hybrid system might use a quantum processor to explore multiple quantum states simultaneously, then feed results to a classical computer for final analysis and decision-making. This hybrid model is gaining traction for applications in financial optimization, supply chain modeling, and quantum machine learning, where immediate utility can be achieved before fully fault-tolerant quantum computers become available. Quantum computers excel at simulating molecular interactions, which are fundamental to drug discovery. Molecules behave according to quantum mechanics, with electrons and atoms in superposition states that classical computers cannot efficiently model. This image shows how quantum computers can simulate a molecule's behavior over time, including non-adiabatic dynamics, where quantum states change rapidly. The graph tracks probability changes that classical methods approximate poorly. Quantum computing integrates into the drug discovery process from initial lead design through optimization. Quantum molecular mechanics simulations help predict binding affinities and toxicity more accurately than classical approximations. The process involves iterative quantum circuit executions to measure energies and optimize drug structures. This quantum-enhanced approach can screen virtual compounds much faster, reducing the need for expensive lab experiments. By accurately modeling how drugs interact with biological targets at the quantum level, quantum computers can identify promising candidates faster, potentially shortening drug development cycles from years to months and bringing new medicines to patients sooner. Simulating the properties of materials at the atomic level is another promising application of quantum computing. Quantum computers can model complex molecular interactions that classical computers struggle with, enabling the design of materials with enhanced characteristics. By accurately calculating electronic structures and bonding behaviors, researchers can discover materials optimized for specific applications, like batteries with higher energy density or semiconductors with faster switching speeds. This approach combines quantum simulations with machine learning workflows to predict material behaviors, accelerating innovation in energy storage technologies and electronic components. Scaling up quantum computers to a practical size represents one of the most significant challenges in the field. While current systems operate in the noisy intermediate-scale quantum era with around 100 qubits, achieving fault-tolerant quantum computing requires thousands or even millions of qubits working together reliably. Building such large-scale systems while maintaining high fidelity and coherence is an extraordinarily complex engineering feat. Coherence refers to how long qubits can maintain their quantum states without collapsing. And as systems grow, this becomes increasingly difficult due to environmental noise and interactions between qubits. Fidelity, or the accuracy of quantum operations, must remain extremely high, typically above 99.9% per gate operation, even as the number of qubits increases. Physical constraints like heat dissipation, precise control of quantum states, and the need for error correction all compound the difficulty. The challenges of quantum computing scalability encompass many interconnected problems, from algorithm development and hardware limitations to the need for trained talent and standardized protocols. Overcoming these obstacles will require breakthroughs in materials science, cryogenics, and quantum error correction techniques. Quantum supremacy marks the point where a quantum computer can perform a task that is impossible for classical computers. This milestone was first demonstrated by Google's Sycamore processor in 2019, which solved a random circuit sampling problem in just 200 seconds. The same task would take an estimated 10,000 years on the fastest classical supercomputer available at the time. While this achievement proves quantum computers can outperform classical ones, the tasks are often artificial benchmarks designed specifically to highlight quantum advantages. They don't necessarily translate to real-world practical applications that would benefit everyday users or industries. Quantum supremacy is an important milestone showing the potential of quantum computing, but it's not the end goal. Researchers continue to work toward quantum advantage for commercial problems, which experts predict could happen around 2030, with further refinements in hardware and algorithms. A shortage of skilled quantum scientists and engineers is a growing concern. As quantum computing advances rapidly, the demand for specialized talent far outpaces the current supply of qualified professionals. This workforce gap stems from the field's complexity, requiring deep expertise in quantum mechanics, computer science, physics, and engineering. The rapid growth of over 200 startups globally is widening this divide. Quantum careers span diverse specializations, from quantum education and algorithm development to hardware engineering and quantum simulation. Each path demands unique skills and knowledge. Career progression typically starts with entry-level technical roles and research positions, advancing to senior strategy and leadership roles as expertise grows. With global investments projected to reach $50 billion by 2030, addressing this workforce gap is essential for realizing quantum computing's full potential. As quantum computers grow more powerful, ethical considerations become increasingly important. The ability to break current encryption algorithms raises significant concerns about data security and privacy. Quantum algorithms like Shor's can factor large numbers exponentially faster than classical computers, potentially breaking widely used encryption methods such as RSA. This could expose sensitive data that was previously secure. Beyond encryption, quantum computing could enable unprecedented surveillance capabilities and compromise privacy in digital communications, IoT devices, and blockchain systems. Harvest now, decrypt later attacks become feasible with quantum power. To address these challenges, responsible development following SEA principles, advancing innovation, engaging stakeholders, and safeguarding society is crucial. ELPC frameworks guide ethical, legal, policy, social, and technical considerations. These ethical considerations extend to geopolitical impacts, where quantum advantages could create imbalances in security and economic power. International cooperation and ethical guidelines are needed to ensure quantum technology benefits society responsibly. Experts predict that quantum computing will continue to advance rapidly in the coming years. While fault-tolerant quantum computers are still some time away, the field is making significant progress, and quantum computers are expected to have a transformative impact on various industries. Looking at the timeline of quantum computing, we've seen remarkable progress from the early theories in the 1900s to quantum supremacy claims in 2019. This foundation sets the stage for continued rapid development. Quantum computing applications are expanding into key areas including artificial intelligence, material research, natural language processing, manufacturing, logistics, drug discovery, finance, and cybersecurity. With investments projected to reach $50 billion by 2030 and global initiatives driving progress, the quantum future promises to revolutionize how we solve complex problems across industries.